In this video, we'll find the volume of a cone using integrals. So this example says, let's find the volume of a cone with radius capital R and height capital H. So the capital R and the capital H are constants here. So they're not variables, even though I don't know what values they are. They represent some fixed number, some constant. So the way I want to begin here is I want to draw the shape, and I'm going to align this shape with axes. Okay, so I'm going to put a bullet point next to this. So let me draw an x-axis and a y-axis, x-axis and y-axis, and I'm going to draw it. So let's say this is x, that's the y direction. I'm going to draw it so that I put the tip of the cone at the origin. Okay, I don't have to do it this way, but I am. Okay, so I'm going to draw the cone, and then I'll have this circular base, and it'll look something like this. So I'm just drawing my cone so that it extends in the x direction, because in the formula that we derived in our last video, we had done it along the x-axis. But if I wanted to, I could also extend this along the y-axis, and it would work just fine. Computationally, it turns out it'll be slightly more work if I had set up my base at on the axis and the tip in the other direction. And that's why I chose to orient my shape like this. But even if we were to sort of flip the direction, we would get it to work. Alrighty. So I know that the radius of the cone, this distance, this is r, and the height is this distance. And if that's the height, we know that at this point over here, the x-coordinate is h, whatever h happens to be. So what I'm going to do now is I'm going to draw one of the cross sections of this cone. So I'm going to slice it vertically. Okay. All right. So when I do that, the cross sections will have circular shapes. Okay, and the back side is going to have maybe something like this. And then, actually, let me draw with a solid line. And now I'm going to give that cross section a little bit of thickness. So I'll give it a little bit of thickness, just a tiny amount of thickness. And now I'm going to connect those. Okay, so I have this sort of disc shape. So a disc is a circle, like I have, but with a little bit of thickness, or a little bit of depth. Okay, so this depth here is in the x direction, and it's really small. So I'm going to go ahead and call it dx. And if I wanted to call it delta x, I could, but when I go to an integral, I'll be using dx. So I'm just using dx from the get-go here, so I can remember, oh yeah, in my integral, I'm going to use dx. So the dx just means it's a change in x, and it's really small. Okay, and one of the things I'll need to figure out is, well, what's the area of this cross-section? So I'm going to label, for the area, I will need to know this radius, which I'm going to call lowercase r. All right, so let me also make a note of the fact that we created an arbitrary cross-section in our diagram. And now what I want to do is I want to find its area. I want to find its area because if we remember our formula for volume, the formula for volume will involve an integral. In this case, it's going to be a dx integral. And the way that I can tell is that the variable here has to do with what direction the thickness of these slices is in. And for my shape, the thickness is in this x direction. So the thickness of the cross sections is in the x direction. And that's how I know it's a dx integral. Okay, and I'm going to be taking the integral of my area function. So this is going to be the area of x. It needs to be in terms of the variable x because it's the dx integral. And what does x go from here? Well, it starts at 0, and it goes until h. Okay, so we are just using this formula that we had in the last video for the exact volume. All right, so I have this integral from 0 to h. The area function, the area of this cross-section, is just the area of the circle, which is pi, the radius we call little r. So we'll have little r, whoops, let's put that in orange. Little r squared. And then we have dx All right. But to be able to take this antiderivative, right now the variables don't match up. I have little r, but this needs to be a dx integral. So we need to somehow relate little r with x. And I forgot to mention this earlier, but at the point where I've drawn my circle, this cross-section, this point, I'm going to call that x-coordinate x. And that's what makes this an arbitrary cross-section. So at some arbitrary x-coordinate, I am drawing that cross-section. So I need a way to relate that. So I need a way to relate x, that variable, with this radius r, lowercase r. So the way I'm going to do that based on this picture is I notice we have some similar triangles. So we have some similar triangles. So we will be able to set up a proportion. So if I draw our triangles, so we have a big triangle, right angle triangle, and then a smaller one. So if I reference our picture up here, so in the big triangle, this vertical distance is capital R. The big horizontal distance is capital H. In the small triangle, that vertical distance is lowercase r. And that horizontal distance goes from the origin to x. So that is just x. Whatever the x coordinate is that distance. All right, so we are now ready to set up a proportion. Okay, so I could do something like lowercase r over lowercase x. So in the small triangle, that would correspond to the big triangle, where I'd get capital R over capital H. So let me isolate little r, and I get little r equals capital R over capital H, multiplying the x over. And now we will be able to plug this into our integral for the little r. So we get this equals the integral from 0 to h. Let me pull the pi to the front because it's a constant. And then I'll get little r squared, which is big R over big H times x squared dx. Let's simplify. We get pi times the integral from 0 to h. This will be r squared over h squared times x squared dx. So this might look a little intimidating because we got, all these letters. But remember, the r and the h were constants. So this whole fraction is going to be a constant. Okay, so at this point, we are ready to take our antiderivative. We will get pi times the r squared over h squared will stay there. And then I'll get the antiderivative of x squared, which is x to the third over 3. Then I got to plug in the h and the 0. All right, so when I do this, let me keep the constant pulled out. Pi r squared over h squared. Let's keep that pulled out. And now let's plug in the capital H into this. So we'll get h to the third over 3 minus plug in 0, which will just give me 0. All right, and if I simplify now, we get pi r squared h to the third over 3h squared. And this becomes 1/3 pi big R squared big H. And that is the formula for a volume of a cone. We have just proven where that comes from using calculus. Alrighty, so in terms of our goals, we know how to find the volume of familiar geometric shapes in the way that we did here. We align it with our axes, we got to be able to create this arbitrary cross-section, find a formula for its area, and then set up an integral.